You wish. This is from lecture 5 examples that I've modified slightly. Yeah. I guess let's get started. Yeah. Yeah. No worries. So I'm going to go through the ALU and some of the code and some of the common problems that people have been posting on Piazza. So a lot of common issues that we've been seeing is inferred latch. Everyone seems to get this error. It's a common issue, and it's a really easy fix. So I'm going to go to my text editor because it's a little better to see things. So we just have a normal ALU. This is from lecture 5 zip file on TritonEd under week 5, lecture 5, under lectures. And I modified it a little bit just to show you a couple of ways to do the same thing. So I added just a CN and cout. That's the same thing as a carry in and carry out that Professor Eldon was talking about. So you definitely want to have that for your ALU. And then another thing that I'm doing different, instead of concatenating a result and storing it that way, I created a 9-bit temporary result. This is totally okay to do just within your ALU. So you can use that extra bit for your shift lefts or your carry outs that happen due to additions. You can, so for an example, if I'm adding two numbers where I have input A plus input B plus Cn, I can store that in temp result, which is 9 bits, because I'm adding an 8-bit value, an 8-bit value, and a 1-bit value. So the most I'm going to get here is 9 bits, potentially. And you can use that 9th bit, or the output of like the result of the ALU, I just use those first least significant 8 bits, and cout is that 9th bit. The other way of doing that is what you saw earlier, which is this, where you can use concatenation, and you can do cout and just out. That would do the same thing. So now that's watching out for your carry out bit, if it happens. So there's two ways of doing that. You can use whatever way seems easier to you. And so in the ALU, you're going to be doing things combinationally. So there's no clock input to the ALU. And you have different cases, like a switch case for each operation. So we're using mnemonics. So if you look at the definitions.sv, we're declaring these constant logic mnemonics, essentially. And what it is that whenever we have this pattern, we want to see this here. And then we're going to be using this mnemonic right here that's going to be really helpful to us in model sim. So instead of looking up a table, 000 is add, it'll just say add u in model sim, or it'll say whatever the instruction is. So you want to update this stuff. So jump back to the ALU. So you have a bunch of different cases. And the issue that happens with inferred latch is that sometimes if you don't have a default, things are just going to be hanging. Like the system Verilog and Quartus won't know what that value will be. So a simple analogy to relate like what this problem is like is imagine having a function that returns an int in like C++, and you have a bunch of if-elses inside that function. And your returns are nested in those if-elses. So it's potential that you won't ever return a value. So imagine if OP was null. How is it ever going to return something? It's just going to latch to a value. So that's like a, not totally equivalent, but a similar analogy of what that of what would happen. So to fix that, you add a default case, and you look at your outputs. Look at your outputs for your ALU. So we have 0, cout, out, and equal. But you don't need to worry about 0 and equal, but you do need to watch out for out and cout. So, oh, I think in this example I took it out. Yeah. Yeah. So yeah, that's what, for this example, you do have a case for out to check to see if it's 0. But the warning that I'm going to get, so if I run it in Quartus right now with some stuff commented out, it should give me an error. Let's try it. Yeah, so it says always com construct does not infer purely combinational logic. So, and it says inferred latch for cout, and it gives you a line number. So it's going to open this up. So if we look at our code, cout in some of these cases, like I'm not setting cout for ksub or kand or kxor or some other ones. So a way to fix that, and this is with a default. I still have a default case. So you would think that that would fix the problem, but not necessarily. So the way that I fix this is to initialize your output variables. So before I even hit the case statement, I set temp result to 0, I set out to 0, and I set cout to cin, because I don't want to overwrite. If I made this 0, I could potentially, depending on your ISA, overwrite that existing overflow value. So I just want to set it back to what it originally was. That's why I have it as cin. So now that I initialize some of these values, it should not give me an error. So let's try compiling again. Cool. So no reds, so that's good. You always want to take a look at the warnings when it's done. Finished. So some of these warnings are you can completely ignore. So if you see no clocks defined in design, don't worry about that for this lab. All these warnings you see here, you can completely ignore. And it says right here, for op mnemonic assigned a value but never read. That's okay because we're using op mnemonic for our tests. We're never reading it within our system Verilog code. We're going to be reading it in our model sim, and when we do our test bench, we're just going to be monitoring what that value is. That's all we're going to be doing there. So does anyone have any questions on ALU that you guys are having trouble with, like specific operations or how to do certain things? Yeah. No, so store word, if you just have an address, like a memory address that you already have, and that's in a register value, it doesn't need to go through the ALU at all. The only reason you want to go to the ALU is to do some operation like an addition, an AND, an XOR, whatever. So if you already have your address, you can just have that wire going from your reg file to data memory as an input to like address. Yeah. A branch, so for a branch, if you're checking to see if two values are equal, like two register values, or if something is 0, you do want to do that in your ALU. So what we do here is we have this equal operation, and what equal says, it's being used by the branch instruction. So all it's doing is checking to see if A equals B, and we're using a little ternary operation where if they are equal, set equal to 1, if not 0. So what you're going to do, if you can just zoom out a little, you're going to have this bit flag that's equal, and you know that instruction might have been like branch equal or something. So your control is going to have a signal outputting that like a branch. And then you have this equal. So you're going to AND those two to tell you to branch or not. And then you're going to feed that back in as an input to your instruction fetch. So you have these You have this instruction that's telling you it's a branch. You have this output of the ALU that's saying, hey, they are equal, we need to branch. And them, and you're going to feed it back. And that will tell your instruction fetch that, okay, I need to do something with my PC to like add it to a target or something like that. So that's what the top level will be like it's like a central controller in the sense that it's wiring everything together. That's what, yeah, and that's what we're going to be doing in lab 4. Yeah, so if we look at this example, just to make it really clean and simple, and I recommend doing it this way, is I just added the files necessary just for the ALU. So for the ALU, I just have definitions and ALU.sv. And then for reg file, I'm just going to have reg file. And for instruction fetch, you can probably add just instruction fetch in your IROM. So I don't recommend adding the test bench files to Quartus because it can get weird sometimes. So just keep test bench, only add those to your model sim project. So
what you can do if you want the test bench in Quartus, just make sure you upload the module you design. Test bench design itself is the same as the project name in Quartus,
yeah.
and you identify that as the top level for Quartus purposes.
Yep.
So, but otherwise, the simplest way you have to test bench.
Yeah.
You obviously have to have the model sim.
Yeah. Just for lab 2, since there's no one has a top level, I just did it this way. Yeah. And then to make things even more simpler, I just create one directory. So like, here's my ALU directory. My Quartus project is in here, and my model sim project are using this same folder. They all have different files, so like most of this stuff is for Quartus, but like this MPF, that's a model sim project file. So I just have everything living in the same directory, because the only things that I care about are the SV files. Other stuff is just what the programs produce. So back to ALU. So everyone good on that? I can move on to reg file, and then I'm going to do instruction fetch, and I can show you guys some things there, and then I'll show you how to do some tests and interpret those. So let me make a project for reg file. I'll do instruction fetch first. Okay. Let's look at these files. So this is, I changed the example that you guys have probably seen where you didn't see assigned before, it was just input target, and then before it was just setting PC to target. So before, if I just leave it like that, this is actually doing absolute addressing. So this is, target is actually telling the instruction fetch, hey, go to this address in your instruction ROM and start executions at that address. So to do relative addressing, you want to do something like this. So with relative addressing, you're adding some value that could be positive or negative to your PC. Negative meaning you want to branch back, positive meaning you want to branch forward. So to interpret a signed value as an input to your instruction fetch module, you want to make the target a signed input. So that's what this does here, where I can take some value that's 8 bits from minus 128 to 127 as a signed value, and then I'm going to be adding that to my program counter. So that's what it does here. So this is just a simple case, not much going on. Most people aren't going to be doing crazy things in their instruction fetch. Does anyone have any questions on this, or on your own ISA, or if you're having a little trouble, I can help you out on that? Does everyone understand this little block of code? All right. So let me show you what the test bench for that looks like. So here's the test bench for that instruction fetch module. So my test bench for instruction fetch combines the test for instruction fetch module and for instruction ROM. So you can do it a couple of ways. So in the lab write-up, you can either make this one giant block where everything, this whole thing is your instruction, or your if.sv module, or you can segment it where you separate the instruction ROM and you make that its own sort of module. You can do either or. There's no pluses or minuses. It's just what you prefer. For me, I like to separate it just because it's a little easier to see like what's happening and what's being output from each respective module. So my IF module just outputs a program counter value. So if we look at my IF module, the only output I have is PC. And if I look at my instruction ROM is really simple. That's how big it is. It's just like a register file where I have an input for an address that's 8 bits. Just for you guys can have more bits here because that depends on how many instructions you have. So the way we're doing it this quarter is that you can load up your memory at the start of every program, so you don't have to load all 3 of them for each program. So you have to determine what log2 ceiling is of your highest program of the static instruction count. So let's say you have 300 lines of assembly code for program 1, 200 lines for program 2, and like 150 lines for program 3. I'm just random numbers. So that means you're going to need 9 bits. You're going to need 512 just because the first one is 300. So set that accordingly. And then that's my input. So I'm going to be tying my program counter. I'm going to be feeding it to this input because that acts as the index for what is in my instruction. And my output is going to be 9 bits, my instruction out. And the way you make your instruction ROM is it's very similar to how you do it in the reg file. So if we look at the reg file, we sort of had this business going on where I have logic. That means registers. And I want to declare how wide those registers are. So for us, our registers and our data path is 8 bits. But for our instruction ROM, our instructions are all 9 bits. So that's why I made it 9 bits here. You give it a variable name, whatever you want, and then I manually just hard-coded in that for this example, the biggest, or the size of my instruction ROM is 256. So if you had 300 instructions, you'd want to make that 512, and you can leave it. If you have empty space, it doesn't matter. It doesn't affect anything. And then what you do is you just want to read out what is in your instructions. So you want to output or set instruction out is equal to instructions and give it the input index. So that's what happens here. Is everyone familiar with this or understanding that? Yeah, so I'll post this stuff again, but it is in lecture 5.zip, yeah. Yeah?
So the size of the instructions array is going to be the size of how many instructions you have with the program size together?
So you don't have to add them all together this quarter. You can just pick the biggest one. So whatever number that is, that's like your ceiling, and then do like power of 2. Yeah, so I'm going to show you guys how to reset it and do all that stuff in the test bench for this. So yeah, let's have a look at that. So here's my test bench. Let me open up Model Sim as well. Oh yeah, let me show you guys one more thing. So the lab, you're doing 3 files, the reg file, ALU, instruction fetch, another 3 files, a test bench for each one. We want you guys to show schematics, and I'll show you how to do the schematics right now. And then in Model Sim, you want to take like screenshots of each test case that you come up with and just like annotate it like, hey, at this time we were doing our add operation. These are the 2 inputs. This is the result we got. It's good. And you want to do that for each operation. And same thing for your instruction fetch. Like you want to test that your halt's working, your start's working, your branch is working if you're doing absolute, or if you're doing relative, you just want to see that it's correctly working there. In your reg file, you just want to see that some control signals aren't broken. So if your write enable is not high and you're trying to write to a register, it should not write. So things like that, you know. So let me run this. Hopefully it'll compile. And I'm going to show you guys how to do the schematic. We posted a walkthrough, one of the TAs. You can do it that way. That's perfectly fine. Let's see what it is. Production, Joker. All right. We have a small error. Let me look at something. Always use the cheat sheet. This is really handy. Oh, they're not showing it in here. Do a quick search, system Verilog, signed input. Ah, it goes after input. Cool, no errors, it's running. Double check the warnings just in case. Oh, that's fine. All right, so now that you have a successful compile, you want to do this for each SV file that you do for your ALU reg file and for your instruction fetch. So what you want to do is look at compile design, and you'll see analysis and synthesis. Click the leftmost little caret arrow right there, and you're going to get a little drop down, and you're going to see netlist viewers. Click the leftmost caret for netlist viewers, and you're going to see RTL viewer. Double click RTL viewer. So what this is going to do, Quartus generates a schematic for us. So you can either do it the walkthrough way where you make your own models, but this is the easy, simple way. Quartus does it for you. I recommend doing it this way. So what you can do is where you make models in Quartus using the walkthrough, and that'll generate code for you. I don't necessarily recommend that because coding it from yourself is like you have total control over it. You know how everything's going to be wired. You know what all your inputs, outputs are. I recommend doing it this way. And so you just want to take a screenshot of this, or you can print it out to a PDF or whatever, and then that's the schematic that we're asking for each module. So you can see for instruction fetch, it's not much stuff. It's pretty simple. It's just you have an adder, you have some muxes, and then a register for your PC. So let me show you guys the one for ALU. ALU is going to be the one that's pretty big. File this. Yeah, ALU is going to show a bunch of stuff because that's a lot of gates in your ALU, depending on how many operations you have. So let's say you're doing like 16 arithmetic sort of things in your ALU, and if you have like your compare string or your pattern match or your Hamming distance, it's going to show a lot of stuff. Yeah.
For your instruction fetch, do you have separate models? Screenshot model?
Yeah, so you would just take a screenshot for your instruction fetch and your IROM. IROM is just going to show you like a little box, and I'll show you what that looks like. So let's see what it looks like for this somewhat basic ALU. So you see a bunch of stuff here. So this ALU is not doing much, you know, it's just adding, subtracting, shift left, anding, and XORing. So yours is gonna look crazier than this. Just keep that in mind. Yeah, so the one for IROM, it's just gonna show a little box with like registers in it. So just take a screenshot of it and add it to the report. So what I wanted to show you guys next was model sim. And I'm going to code some of these tests for you guys so you can see what's going on, and I'll show you live how to do it. So let's have a look at our test bench. So our test bench, you want to just declare a module and put underscore TB. That's just the name we're giving this module. And then we're going to have inputs and outputs. The inputs are all going to be bit, as you can see here, and the outputs are going to be wires. So these inputs, it's easy to make it match the same name as the inputs of your instruction fetch module. So you can see we have a branch, target, init, halt, clock, PC. And then if we look at our test bench, they're spelled exactly the same. If you spell them exactly the same with the same case, you don't have to do this business where when we declare an instance of that instruction fetch module, you don't have to type in the name. So let's say that branch here, or here, I mean, is like lowercase branch. And then over here, I declared an input called branch. So this would be incorrect. So I would have to make it and manually specify what bit is being connected. But if I have them the same case and the same spelling, I don't need to do any of that. I can just leave it as branch and make sure it's the same back over here. So now that they're the same, you don't have to do that parentheses business where you have to specify. The newer versions of Quartus, I believe 14, 15, 16, will take care of this automatically. The older ones might not. So sometimes it is good practice to specify in parentheses, even if they are the same. But the newer versions will take care of it for you. It'll infer it if they're the same. So what this is doing is just instantiating. So think of your instruction fetch as like a class, like object-oriented style, And think of this UUT business as a instance of that class. So we call or use the same name of the module that we have here, so IF, all caps, and then we give the instance name a name. So for this one, since we have different instances here, I like to specify which one it is. So I call this instruction fetch underscore UUT, UUT meaning unit under test. And then I don't need to connect anything because I have the same inputs and outputs. And then, so I do have one extra output. So we know that the IF module is outputting a PC, and we know that the instruction ROM is outputting INST out. So I created another wire called INSTR, and I have to connect that here because it's different. And I have to connect the PC wire. So this PC is actually doing this. Even though the same name, the output of this module is connecting to this wire. And then this wire I'm using as an input to my instruction ROM. That's what that means. And then I'll explain what this code means. So once you've created or instantiated whatever you want to test, you want to put an initial begin block. So ignore all this stuff right now. You want to have an initial begin and end. And then you always want to end with the end module. So for instruction fetch, I'm testing the loading in of a text file. So I have a text file here called machine code. So in lab 3, you're going to be making your assembler where it's going to take your assembly code and produce something that looks like this, where it's just 9-bit ones and zeros. You're going to probably have 3 files, one for each program. So this one, for example, is just 170 instructions. So what the test bench does here is I'm using this command. This is a system Verilog language construct called $readmemb. So readmem, where I'm reading a file and I want to load it to in memory, and B for binary. You can also do hex, or if I did readmem H, but the difference would be that my machine code would have to be in hex format. So all this is in binary format. That's why in the test bench, it's B. That's the difference. So you could do like 00A0, something like that, or like since everything is 9 bits, you're going to have like some You're probably going to have a 0 or a 1 for the first hex digit, and then you're going to have whatever else hex digits there are, 4 and 4. So, yeah, go for it. No, go for it. Do you have a question?
I was just gonna ask. I was kind of lost when you said PC and
Oh, these two?
yeah, like what's the difference between them?
So we know that our instruction fetch module, there's an output for PC. And if we look at our instruction ROM, we have an input for address. They're essentially the same thing. But we have two things here, and we need to connect them. So this is outputting a PC. This is taking an instruction address. So in our test bench, I created this wire called PC. And what it does is that I connect the wire from my IF module's PC, and I feed it, and I connect the other end to the instruction ROM's instruction INST address. So now there's a wire going from my IF. Yeah, exactly. Yeah, so that's all it does. And then I create another wire so that we can see what the actual instruction is. I don't need to do this for the test bench. You can look at it, like zoom in, and I'll show you how to do that. But this is just puts it on the top for me.
So you can like actually read the value?
Yeah. You don't necessarily need this, and I'll show you how to do it without it and with it. This just makes it cleaner. But it's not incorrect to not have this one. And so we do a read memb, and the first argument you want to specify is a text file. So make sure it's in the same directory as your project, your model sim project. So here's my if_tb.sv, and here's my machine code file. So they're in the same directory, so I don't need to do anything. That's cool. And then the second thing you want to, the second argument that you're going to give is the actual name of the instance of instruction ROM. So irom_UUT, and I use this dot operator for instructions. The reason it's dot instructions, if we have a look at our instruction ROM, we have this logic block, and we named it instructions. So this is like a member variable for this class. So we use the dot operation to give us X-ray vision to look at certain things. So what it's doing is it's going to load all these ones and zeros from machine code text and load it up into that array of instructions. That's my IROM. So that's what that's going to do. And then just to check that it did it correctly, I'm using a for loop. And so $display, that's like a printf statement, you know, if you want to check certain things somewhere. You don't want to put these in your non-test bench files, only put them in your test bench where you want to print and check things. So I'm just checking to see that it read it correctly, and I can see binary and hex. And then you always want to do #100 sign or #100 ns. That just, you always want to give your test 100 nanoseconds just for the simulation to clear up, and then you start doing tests here. So I'm going to add some test cases. So if we look at our instruction fetch, we have branch, target, init, halt, clock, PC. So the first thing I probably want to do is set init equal to 1. And if we look at what init does, let me split these. So init just sets the PC to 0. So yeah, that's cool. Let's just set our PC to 0. And then when you're doing your tests, you always want to make sure that other inputs, depending on how you coded your instruction fetch, if it won't affect it. So if init is 0 and everything else, if it's like a don't care, it's not going to be affected because this conditional is just looking at init. So if we look at our period, it's 10 nanoseconds. So if I wait 10 nanoseconds, my PC in this clock should be 1. So if we're starting at 100 here, between 100 and 110, it's going to set my PC to 0. Between 110 and 120, we should see PC of 1. So I'm just going to write a comment. PC should be 1. And then from 120 to 130, we can test if our branch is working correctly. So to test if branch is working correctly, branch is a control signal here. So we want to set branch equal to 1. And then we want to give target a value. So target, we'll just give it a positive value, and the next test we'll test to see if we can jump backwards. So, but since we're at 1 here, we want to, and then it's going to do +1 here. Let's just jump 8, and we should be at 10. And when you're writing stuff in System Verilog, so for control signals, it's okay to write zeros and ones, but when you're writing numbers, there's always follow like the convention of writing correctly. So if we look at target here, target is an 8-bit entity. So 8 bits for 8. So 8 apostrophe. So there's a couple of ways to do this. You can either just give a binary number, but I'm not going to, we all know what 20 is in binary, but let's say I want to do like 47 or something, I'm going to have to convert it. So you can either do some binary pattern, give it 8 bits or whatever, or you can give it 8 apostrophe hex and specify some value, or you can do 8 apostrophe D and give it a decimal value. So that means the value of +8 as a 8-bit thing. And then I'm going to go 10 nanoseconds. Now I want to have a test where see if I'm branching backwards correctly. So I'm going to give branch signal assert it again. So I'm going to make it 1. And then I want to make my target some negative value. And we should see the PC being affected accordingly when we run the test. So let's make it some negative number, -5. And then always end your test with $stop. So that will tell the simulation to like say, hey, stop here. And then let's add another test in here. Why not? Let's test to see if halt is working. Oh, one more thing. Another thing that I did last quarter. So you see how I set init equal to 1 here? It might stay 1 in your test. So look at your control signals and reset the ones that you don't want to be affected. So I want to make init equal to 0. Or sorry, I actually want to put that here also. This is how I did it. I mean, sometimes it's paranoid to do this, but it's okay to be a little paranoid. That's what I did, where I would always set things back to like 0, and I would make sure that each test that I'm doing is like for sure that's what I want to test. So I definitely need to add a halt equal to 0. Target doesn't matter because we're only using target if branch is asserted. Cool, let's test this. So I'm going to go back to model sim. Let's see if it compiles first. Oh, we have one error. So let's see what it is. So you can double click the error and it'll show you what it is. Oh, undefined variable I in test bench. Oops. So remember I had that for loop here? I'm trying to remember how to do this. There's a certain way to do for loops and tests. Oh yeah, there we go. That should do it. So it's just like writing C code or C++ code for your test bench. Generally, you can't do that in System Verilog though, but it's okay for a test bench. What? Ah, good catch. Save that, see if it compiles. Cool, no errors. So you should see all green check marks showing up. So to simulate, you want to go to Simulate, Start Simulation, hit Work, and select the test bench, because the test bench here is acting as like a top level file. Hit OK. It's going to do all this stuff. So here's a bunch of stuff that we have. So I definitely want to see all these control signals in clock. Add wave. Definitely want to see all that. So you see how I'm doing it. I'm just right-clicking on all the things that I want to monitor for each clock cycle. I want to see what my instruction is. Definitely want to see what the PC is. Make this guy to the bottom. So I want to see these values as binary, and I want to see this guy as a decimal. And then one other thing, so if we look on the left side, so remember we had our if_tb module, that was our test bench, and then we instantiated an instruction fetch module and a IROM module. And we call them if_uut and IROM_uut. You can see those right here. So if I click that and I look at my object view, this is showing me all the variables inside the IF module, and same with IROM. So a cool trick another cool thing to see if things are loading correctly, and also with the registers. So in your register file, when you do your register file test bench, you can look at your UUT for the reg file and have X-ray vision on your registers. So remember, my instruction array was 256 things. I can see all 256 of them. And I want to add that to my waveform. So I can go add wave, and I can see a whole bunch of stuff. And I want to see these as binary. So when I run this, I should see it load that text file into my IROM, and it should print out the contents that got loaded, and it should run these tests. So let's run it. Cool, it ran, and you see a little breakpoint arrow that shows up at your $stop. That's what you want to see. Want to go back to wave. It looks all weird because the time is all off right here. So you see it's like 149.2 or something. It's hard to read, sorry about that. You always want to hit the blue magnifying glass button. That's just going to auto set everything for us. And then if we look at our output window here, so since, remember I only had 170 instructions, they all got loaded correctly. We can see all that here. So we see the binary format and we see the hex format. So we see all that. And then another thing that we want to see is if we were branching correctly. So over here, we started our test at 100 nanoseconds, and PC was 0, that's good. And then we jumped forward 8, so let's make sure that that's what our code is doing. So we started at 0, the branch and halt to 0. It should have incremented here. Oh, I know why. I'm just adding another period in there so you can see it go from 0 to 1. So the reason I'm adding init equal to 0 afterwards is that giving it high real quick is going to reset, and then setting it back to 0 won't affect the rest of it. So since I made changes, you always want to recompile. Hit compile all. Make sure there's no errors. You always want to do restart right after that. You can leave all these checked. Hit OK. It's going to reset everything, and then we want to hit run all again. It's going to go back to our breakpoint, and we want to see what happened here. So one thing that's weird is that init went high at 100 and some other time. It's weird. Sorry about that, guys. Just trying to see what it's doing. We should see init be asserted at 100 nanoseconds, but it didn't. It's probably because I added the 0 right after it. So what it does in model sim, it's almost doing it instantaneously. So it went from 1 to 0 because I had init equal to 1 and init equal to 0. So model sim interpreted that like, let's just make it the later value because it's still within one period. So don't do something like that.
Oh, you have to think one clock tick?
Yeah, exactly. Because it was still within like 10, because our period is set here. So our period is 10 nanoseconds. Yeah.
So it's exactly.
Yeah. So it just like, hey, let's just make it that one value.
It's a little longer during the time, right?
Yeah.
Just a little longer.
So let's recompile. Restart. Run all. The little blue button. All right, so we see it go to 8, and we see it become -5. Oh, that's why. There we go. So it becomes 0, 1, 2, 10, and 15. I made it positive, but let's see if when we make it negative. Sorry, time's almost up. This is the last one I'll do. So you see that I made a real simple error where I was looking at target. Target is just the value I'm supplying. I should have been looking at PC, but I didn't set that radix correctly. So watch out for these little small things, you know? So you're just gonna have to play around with it and experience it. But we start at 0, it becomes 1, becomes 2, then we branched forward 8 instructions, so our PC became 10. And what you want to do is you actually want to see what your instruction out is, like what the value is compared, and compare it with their line number. And I had a -5 for my target, which is branched backward, and we see PC became 5. So it worked. Yeah, that's it, guys.